Hi, this is Ashim Datta. I am a professor in the Department of Biological and Environmental Engineering at Cornell University. This short module is in a series intended to help recap the math that might have been done a year or two earlier before taking an undergraduate course in heat conduction or mass diffusion. This particular module will solve the homogeneous heat conduction equation in 1D in Cartesian coordinate and with a value given boundary condition on one end, but a different boundary condition where the derivative is given in terms of value on the other end. So here is the equation that we are trying to solve, and that equation in the past has been solved, or you can check easily for if you have the boundary condition of value given on one end. So at x equal to 0, temperature is, or variable T is equal to T1, and at x equal to L, the variable T is given as T2. For this condition, it has been solved before, or you can try it yourself. Then the solution is this one. So the point here is, even though we're going to use the same boundary condition of T at x equal to 0 is T1, we are going to use a different boundary condition on the other end. And because of this different boundary condition, we will of course get a different solution. Okay, so let's try the solution process. D squared T dx squared equal to 0, we can rewrite as d dx of dt dx equal to 0, which means dt dx is a constant, C1 is a constant, and so we write t equal to C1x plus C2, where C2 is another constant of integration. And so then these C1 and C2 are the unknowns, and we evaluate C1 and C2 by using these two boundary conditions. So by using the first one, BC1, we get, let's see, T1 is equal to C1 times x equal to 0 plus C2, which gives me C2 equal to T1. So C2 is known now. Now let's use the other boundary condition. Okay. Now you notice it is a bit different. So we could write minus k and then dt dx at x equal to L. So my t is C1x plus C2. So my dt dx is of course C1 as we had it here. And so minus k times dt dx at x equal to L is going to give me C1 because it's a constant, and is equal to h times now t at x equal to L. And this is the stage somebody might write TL minus T infinity. By the way, all of these quantities k, h, T infinity, they are constants for our purpose. But when we do the physics of heat conduction, they have very clear physical meaning. Okay, back to here, then we write it as TL, and if we do that, then we really get in trouble, because what is TL? It's kind of meaningless. We're not given a variable called TL. So this is a new variable that we bring in. If we bring in, then we have to find additional equations to solve it. And so let's try to do this stage carefully again. So I write minus k times dt dx at x equal to L, again the same, C1 is equal to h times t at, so let's look at this carefully. What is the meaning of this term, t at x equal to L? It means my t, which is this, is my t, this t evaluated at x equal to L. So t evaluated at x equal to L, I can even rewrite that C1x plus C2 at x equal to L. This is what we need to write, and then minus T infinity. So this other one is just plain wrong, because it's bringing in some other variable that we have not even defined. It's just wrong. So once we write this, this is equal to h times C1L plus C2 minus T infinity. So if we further simplify this, we write minus k C1 equal to C1 times HL plus H times C2 minus H times T infinity. And so bringing all the C1s on one side, C1 K plus HL is equal to H times T infinity, bringing these two on the other side, H times T infinity minus H times C2. Now of course we can put in H times T infinity minus H times C2 is T1. Okay, so C1 is H times T infinity minus T1 over K plus HL. C1 equal to, and so my T is equal to C1x plus C2. I can rewrite that as H times T infinity minus T1 divided by K plus HL, plus C2 is T1. So this is my solution now. So every time I get a solution, I really try to see if it satisfies the boundary condition, because I can always make a mistake. By the way, there's already the X missing here. Now I know we carefully did this solution, right? This one here. We carefully did the solution. But still, once we have a solution, we should make sure that it indeed satisfies the boundary conditions. We could always make careless mistakes. At least I do. So the two boundary conditions are, boundary condition 1 was t at x equal to 0 is t1, and boundary condition 2 was the convective boundary condition, so it is minus k dt dx at x equal to L is equal to h times t at x equal to L minus t infinity. Okay, so if you think of a diagram like that, this is my x equal to 0, this is x equal to L, and this boundary condition is on this surface. So let's see that the solution we got indeed satisfies these two conditions. Okay, so first we plug in x equal to 0. That obviously, if you plug in x equal to 0, you get t equal to t1. So this first one is definitely satisfied. Now let's try the second boundary condition. So we write minus k times dt dx. So this is my temperature equation. So I take the derivative, which is h times t infinity minus t1 over k plus hl. Okay, that's my dt dx at x equal to L, but there is no more x, so it's a constant value. So that's the left hand side, and the right hand side should be h times t at x equal to L. So t, again, this t at x equal to L is h times t infinity minus t1 over k plus hl times L at x equal to L plus t1, that's my t at x equal to L, minus t infinity. Okay, so we just have to simplify both sides and show that they are indeed equal. If they're not, then we have a problem. So this side, I leave it as is. Okay, k plus hl. And on this side, I get h times, so if I factor out t infinity minus t1, then I get hl over k plus hl. Okay, so that's the first term. And if I took t infinity minus t1, then the second term, I take these two together and flip the sign. Okay, so this is equal to h times t infinity minus t1 times hl minus k minus hl over k plus hl times this, and so that's equal to, these two cancel, so I get minus, this minus I bring in the front, and minus h times k over k plus hl times t infinity minus t1, which is exactly same as this guy here. So both sides are equal, which means the boundary condition 2 is satisfied. We should do these every time we do an analytical solution and get an expression like this. We should really check whether the boundary conditions are indeed satisfied, because as I was saying, it's very easy to make some small careless mistakes. Thank you. To summarize then, we want to recall what we just did. We solved this equation for one boundary condition like this on one end and the other boundary condition of this at the other end, and then the solution was given by this. So there are two things we should remember in particular. One is obviously change in boundary condition changes solution. So the solution now is different from the case where the boundary condition was value given on both ends. The other interesting part is this boundary condition is just a little bit tricky to use because here is the derivative of the function is related to the value. It just have to be done in a more careful way. That's all. So thank you.